We are now recording, so let me go ahead and share my screen and to show you guys what's in Schoology, and then get ready to go over the lesson. So I'm going to share my screen. Okay. So in Schoology, I'm going to click on the Materials tab. Okay. And remember, we are in the fifth 6 weeks. It is March the 29th. Okay, and today is a Monday. Okay. Now, we are still talking about waves. Remember, we started talking about waves and harmonic motion about a couple of weeks ago. We're continuing our conversation into waves. Specifically on today, we're going to be talking about what is known as standing waves. Standing waves is the topic for today. So what I'm going to do, I'm going to put on a brief video that explains what standing waves are. We're going to go over a few examples from this PDF file, and of course, if you pay attention to the examples that we go over for the from the PDF file, you should be fine on working on the standing waves assignment. And I'm going to open up the standing waves assignment as soon as we get done with this class. Okay. So I see some students are just now coming in. Let me go ahead and put the attendance form in the chat box. Please get that filled out if you're just now coming in. Okay. Now, before I put on this video that really does a good job of explaining what standing waves are, I kind of want to show you guys what standing waves actually look like. It's a really good idea just to get a good visualization of how they look like first, before we discuss the physics behind them. Well, right here in this video clip, I have a tank of water. Okay, so guys, I'm gonna play this video clip, and I want you guys to notice how waves are going to be produced in this water. So if you notice here, like at the back of this tank, this person here that's standing right here at the back of this tank, they're going to be, basically sending pulses of energy, traveling through the water. It's almost like hitting, hitting the back of the tank and sending pulses of energy. And as you guys notice, notice how as they send those pulses of energy, can y'all see how the waves are traveling from the back of the tank to the front of the tank? So right now we see a traveling wave created. But guys, in just a moment, you're going to see a standing wave appear. Give it just a moment. Just a moment. And now, can everybody see the standing wave? So notice how the water is, looks like it's just jumping up and down, up and down. This is what is known as a standing wave. And of course, the reason why we call it a standing wave is because look at it. It appears to just sit there. It just sits there, just bobs up and down. So this is what a standing wave looks like. Basically, guys, in order to produce a standing wave in this tank of water, and of course, here's a zoomed in version of the standing wave. But basically, in order to produce a standing wave of this water, you have to hit the back of this tank, just the right frequency. Now, that frequency, those pulses of energy has to be just right to produce the standing wave. And as you guys can see, this is why we call it a standing wave. It's because notice how the water just sits there, but it's just bobbing up and down, up and down. So that is how a standing wave looks like. Now, in this video that I'm about to put on, this guy from Bozeman Science, it's a short 7-minute video. He does a really good job of explaining how standing waves are produced. Okay, we're going to watch this video, and then we're going to work out some examples, and then you guys will have enough information to do the assignment on your own. Okay, so let me go ahead and share my sound.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 115. It's on standing waves. Standing waves are like they sound. They're waves that appear to stand still. And so an example of a sound standing wave is the waves found inside a vuvuzela. And so you blow on it, you get that sound. You blow it with a higher frequency, And then you could even try to pierce your lips a little bit more and get an even higher frequency. But what's happening is you have these specific standing waves that sit within the chamber of the vuvuzela. Now, a wine glass works the same way. If you rub your finger with a little bit of water around the surface of it, what you can do is generate these standing waves inside the wine glass. What you're doing is vibrating the sides, and as you do that, you're vibrating the air, and since you have a standing wave inside there, it makes this pitch. Add water to it, and you're going to have a slightly different pitch. And so waves can either be traveling or standing waves. Traveling waves will move from one place to another, and standing waves will appear to stand still. Now, when you look at it, it's kind of an illusion. They're standing still, but the traveling waves are bouncing back and forth. In other words, they're being reflected off the boundaries, and then there's interference to create these standing waves. And so if we look at this animation, the dark wave is going to be the standing wave, but in the background you can see the blue and the red waves that are bouncing back and forth, and it's the summation of them that creates the standing wave. Now if you notice, that standing wave is going to have areas where it's not moving at all, and that's due to destructive interference, where the waves are canceling each other out, and we call those in physics nodes, areas where it's not moving. And then we're going to have total constructive interference in certain areas, and we call those antinodes. That's where it's moving the maximum amount back and forth and back and forth. And so an example of this could be found in instruments, for example. So a string instrument is going to be fixed at either end, and this animation is a good example of that. It's fixed on either end, and as the waves bounce back and forth, you create these standing waves. If we shorten that, like on a guitar, then we can get different pitches. A tube is going to be the same way. A tube could be open on both ends like a flute, or it could be closed on one end like a vuvuzela, and that's going to create these standing waves as well. So let's start with traveling versus standing waves. And so this PHET simulation, I'm generating some waves. Those waves, and this is just kind of theoretical, are moving out the door, and then they've moved on forever. But if we add a boundary on the other side, in other words, if we add a fixed boundary, you can see now there's a reflection back. So those waves didn't just keep going, they bounce back, and now they're going to bounce back again. And as that wave goes back and forth, you can see that we're starting to generate these standing waves. And you can even see those nodes and those antinodes. In other words, those areas where it's not moving and those areas where it's moving quite a bit. So this is an animation of standing waves. And so what we're doing is, as the blue wave moves to the right, becomes the red wave, which moves back to the left, and it just keeps going and going and going. We're getting destructive interference. That's causing these nodes where they cancel each other out. And then we have constructive interference, and that's creating these antinodes, where those two waves add together to make a much bigger wave. Now, an example of this, if you've ever played baseball before, when you hit the ball, sometimes you'll hit it and the bat will kind of buzz in your hands. In other words, it vibrates quite a bit. And the reason why is that you're hitting the ball on an antinode, an area where the waves going up and down the bat are actually constructively interfering to create a huge vibration there. And we refer to it as the sweet spot, the spot on a bat where the node is, where you don't have much vibration, that you hit the ball and you don't feel really any vibration at all. And so let's go through experimentation. So this is a SimBucket simulation. What we're doing is looking at standing waves. The first one we're going to look at is when you have two fixed ends. So an example of this could be a guitar. And so what you do is you have a string, you hold it on one side, and then you pluck it, and you're going to have vibration. So what do you get? Waves going back and forth and back and forth. What's the standing wave then? The standing wave is going to be that green wave in this simulation. It's that wave that is the addition of the other waves. What's interesting in a guitar is that you don't only have one, what we call harmonic, or one standing wave, but you can have multiple standing waves. Now, in all these standing waves, what makes them the same is that we have a node on either side. In other words, there's no net movement on either side of that string. If we look at an instrument like a tuba or a vuvuzela, what is the characteristic of that? Well, we're vibrating it, but you can see that on the left side we have a node. It's not vibrating, but we have an antinode at the right side. So in each of these harmonics, the left side is going to be a node. It's not going to move at all, but the right side is going to be an antinode. And so we still have those traveling waves going back and forth and back and forth. It's just that one of those ends is free to create an antinode, and then we just have reflection off of that end. These are all the different harmonics. What keeps them all in common is the node on the left, antinode on the right. If we then look at something that has two open ends, like a flute you don't blow in one end, You're blowing on the top to create the vibration, or a pan flute would be an example of that. And so what's going to create the standing wave here? Well, in this first harmonic, we have the node in the middle, and then we have antinodes on either side. Now we have two nodes near the middle, antinodes on the side. So what's the characteristic of a standing wave in a chamber that has two open ends? It's always going to be an antinode on either side. But depending on the frequency, we can get different pitches as we blow through. Rubens Tube is a really cool example of that. In a Rubens Tube, what you do is you fill up a chamber with gas, a gas that's flammable. And so this guy's lighting the chamber. So we're having flames coming out of the top. But on a Rubens Tube, you put a speaker on the side. And what that speaker does is create these longitudinal waves. Those longitudinal waves, as they move through, will create areas where there's a lot of compression. And in an area where there's a lot of compression or antinodes, then the gas really can't make its way out. And so it'll be really low there, but at the nodes, it'll actually come out quite a bit. And so did you learn to predict the properties of standing waves? They result from reflection of these traveling waves. Could you collect data? Again, I use the SimBucket simulation to do that. And then finally, could you describe examples of when this occurs, standing waves? Musical instruments are good, baseball bats are great, and I hope that was helpful.
All right, guys. So I know he went over a lot in that video. What I'm going to do, I'm just going to take the main parts of that video and just kind of sum it up, and I'm just going to focus on the main things that you guys need to know in order to do the assignment. But I wanted to show that video because standing waves are you really have to see it to really get it. And so in that video, he went over lots of real-world examples of standing waves, and so which is why I like that video. So I know he talked about a lot, but I'm just going to go through and just sum up just the basics of what you all need to know in order to do the assignment. Okay. So let me go ahead and share my screen. So, in the video, one of the things he said that, like, if you had a guitar string, and you had a guitar string which was fixed at both ends, and you pluck that guitar string, you can easily produce a standing wave in the guitar string. And so here's an example of how a standing wave would look like along a string. Now, in the video, he gave two important terms, and I need for you guys to know these two important terms: nodes and antinodes. These are very important terms that you guys need to know: nodes and antinodes. Let me write down what they mean so that you guys, whenever you're working on the assignment, you guys will be, you guys will know what you're doing. Okay. So, as he said in the video, anytime you have a standing wave, along that standing wave, the areas where the waves don't move, we call that a node. So guys, look at this point right here. If you look at that point right here, the wave is not moving at that point. If you look at this point right here, the wave is not moving at that point. If you look at this point right here, the wave is not moving at that point. And that point, and of course I'm trying to get this spot on, and then also that point right there. So in red, nodes are basically nodes are points where the wave doesn't move. In other words, they're the areas where you have no displacement. Okay, no displacement. In other words, the waves aren't moving at all, or the string isn't moving. So if you guys notice, along those 4 points there, if you look closely, like right along these 4 points, there's no movement of the string, right? So at that point, you have no displacement. But guys, I want you guys to notice these points right here. Along this line right here, notice I have maximum displacement there, maximum displacement there, maximum displacement there, and maximum displacement there. We call those points the antinodes. So I'm going to write that down. So the antinodes, those are the spots where our wave is moving. In other words, where our string is moving. So antinodes. So antinodes, these are the points of maximum displacement. Maximum displacement. Okay. So, so everybody got that? The definition of nodes are the points of no displacement, and antinodes are the points of maximum displacement. But by the way, the way you remember the definition of a node, the way that I think about it, I just look at this. I see node, no, node, no. So no displacement, no movement. Node, no, node, no displacement. Okay, no displacement, no displacement. And obviously, an antinode will be the opposite of that. Okay, so node, no displacement. Okay, so those are the points along the string where the wave isn't moving, and the antinodes are the points where we have maximum displacement. So guys, remember that for your assignment. Okay. Um, One of the other things that he talked about in the video, he also talked about harmonic number, and let me go to that briefly. Okay. Guys, so here's a wave. Imagine here's a guitar string vibrating at different harmonics. Okay. Guys, for a guitar string that's vibrating at the first harmonic, okay, it is always true that that wave has one antinode, as we see here. Okay. If it's vibrating at the second harmonic, it has two antinodes, as we see here. If it's vibrating at the third harmonic, okay, it has three antinodes, as we see here. So you guys get the pattern. So if you have a wave that's vibrating at the fourth harmonic, it would have four antinodes. If you have a wave that's vibrating at the fifth harmonic, it would have five antinodes. If you can imagine a wave vibrating at the 100th harmonic, it would have 100 antinodes. So hopefully you guys get the basic pattern. So I'm gonna say that again. Okay, for any wave that's vibrating at the first harmonic, okay, it has one antinode. Okay. Okay. For a wave vibrating at the second harmonic, it has two antinodes. You guys see it. It has two areas of maximum displacement, right? Third harmonic has three antinodes, and then fourth harmonic, four antinodes, and so on and so on. So guys, whenever you're working on your assignment, if you want to know the harmonic number, all you have to do is just look at the number of antinodes in the animation. Okay. And by the way, just so you guys know that the number of nodes will always be one more than your antinode. So obviously, if you have one antinode, you're going to always have two nodes. If you have two antinodes, you're going to always have three nodes. Okay. So if you have three antinodes, you're going to always have four nodes. Okay. So just want to be sure to state that. All right. So with that said, guys, let us look at the PDF file that I have posted in Schoology. I'm just going to go over a few things with you all, and then I'm going to work out a few examples, and then I am going to open up the assignment. So pay attention to this because this is where we get into the math. Okay. Now, so as you guys can see, on number one, we have a guitar string that is being plucked here. So you guys can see the first picture shows us the first harmonic. The second picture shows us the second harmonic. This picture shows us the third harmonic, fourth harmonic, and fifth harmonic. So you guys can just see the basic idea, okay? Right? Because first harmonic, one antinode. Second harmonic, two antinodes, and so on. Okay. Now, guys, let us get into some math here. Okay. So, guys, imagine that we have a guitar string, and the guitar string at its first harmonic is vibrating with a frequency of 6 hertz. Okay. So, guys, here's what I need for you guys to know. If you want to know how to move, if you want to know your frequency at each harmonic, all you do is multiply the harmonic number by the frequency of the first harmonic. Okay. By the way, we call this here our fundamental frequency. So, for example, as you see here, if we have a guitar string, that has a fundamental frequency at the first harmonic of 6 hertz, And the second harmonic would be 12 hertz. The third harmonic would be 18 hertz. Fourth harmonic would be 24 hertz. Fifth harmonic would be 30 hertz, and so on, right? So here, this is just 5 times the original frequency, 6, and then 5 times 6 gives me 30. Okay, with that said, let us look at some more examples. Okay, let us focus on number 2. Okay. On number 2, we have a guitar string. Okay, and it's vibrating at different harmonics. So here's the first harmonic. Here's the second harmonic. Here's the third harmonic is already written in for us. This is the fourth harmonic, and then this is the fifth harmonic. Okay. Now, guys, notice here they tell us that at the second harmonic, the frequency is 20 hertz. So that means, what is its fundamental frequency? You would just do 20 divided by 2, and we learn that the fundamental frequency is 10 hertz. Okay, so 10 hertz is our fundamental frequency. Okay. What about the frequency of the third harmonic? The frequency of the third harmonic, I would just do 10 times 3, and that would give me 30 hertz. Okay. The frequency of the fourth harmonic is just 4 times 10, which gives me 40 hertz. So you guys get the basic idea. Let me make this bigger. What about the frequency of the fifth harmonic? It will be 5 times 10, which is just 50 hertz. Okay. All right. I'm not going to work on all of these. I'm just going to do the ones that are necessary for you guys to understand how to do the homework. Look right here where it says mark the nodes and the antinodes for harmonic 2. Okay. So guys, look at harmonic 2. Okay. So if you look at number 2, harmonic 2. Okay. So if I had to mark the nodes, okay, so right here, this point right here, this point right here, and this point right here, those will be my nodes. Okay. And then the antinodes will basically be this point right here, also extended here. So, and this point right here, which is also that point right there. So, in blue, and the other blue there are my antinodes. Okay. So either this point or this point is an antinode, and that point or that point is an antinode. Okay, so my antinodes, these are my points of maximum displacement, and then that point, right, that point, those are the points of no displacement in the nodes. Okay, now let's keep going. Okay. Look at number 3 here, guys. And again, I'm not going to work on all these. I'm just going to do enough for you guys to get the point. Okay, so again, first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. Okay, the first harmonic is always what is known as the fundamental frequency, or the fundamental harmonic. Okay, however you want to say it. So this right here will be the second harmonic. This right here will be the third harmonic, fourth harmonic, fifth harmonic. Okay, so now guys, notice what they tell us. They tell us that the frequency at the fourth harmonic here in this particular example is 80 hertz. So if the frequency is 80 hertz at the fourth harmonic, how can we find the first frequency? In other words, the fundamental frequency. Well, it's easy. We just do 80 divided by 4. So 80 divided by 4 gives me 20 hertz. Okay. kind of zoom in here so I give myself enough room to write. Okay, so what about the what is the frequency of the second harmonic? Well, what's 20 times 2? 20 times 2 is just 40 hertz. Okay. What about the frequency of the third harmonic? It would be 20 times 3, which is 60 hertz. Okay. What about the frequency of the fifth harmonic? It will be 50 times 20. I'm sorry, not 50 times 20, but 5 times 20, which is 100 hertz. Okay. So hopefully you guys get the point. Look at number 1. Number 1 says here. Number 1 says mark the nodes and the antinodes of the fourth harmonic. Okay. So guys, look here at the fourth harmonic here. So if I had to mark the number of nodes, okay, I would have a node here, a node here, a node here, a node here, and a node here. Remember what a node is. The node, that's the point of no displacement. So the nodes are the point of no displacement. The antinodes are where we have maximum displacement. So that's an antinode there. That's an antinode here, right? So, you know, this point and that point, you know, that's really one antinode, but you guys see where I'm going, right? The antinode could either be, you know, at this point or that point, this point or that point, this point or that point, this point or that point. So antinode, 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 antinode. Okay, those are where we have maximum displacement. Okay. So just so we're clear, guys, I want you guys to see that here we have 1, 2, 3, 4, 5. We have 5 nodes. So we have 5 nodes, which means we will have 4 antinodes, right? So 1, 2, 3, 4. The fourth harmonic always has 4 antinodes. Okay. Okay, let us keep going. Again, I just want to work out just as many examples as I can. So look at number 4 here. Okay, so looking at number 4, so first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. So let's go ahead and fill this in. So that's our fundamental harmonic. This is our second harmonic, third harmonic, fourth harmonic, fifth harmonic. Okay. Now guys, in this particular example here, they tell us that the third harmonic has a frequency of 33 hertz. So what is our fundamental frequency? Well, we'll just do 33 divided by 3 to get the fundamental frequency. 33 divided by 3 is equivalent to 11 hertz. Okay. So that's equivalent to 11 hertz. So let's keep going. What is the frequency? In this case, what will be the frequency of our second harmonic? So what's 11 times 2? Well, that's 22 hertz. Okay. Move on to the fourth harmonic. What is 11 times 4? That would be 44 hertz. Okay. Moving on to the fifth harmonic. What is 11 times 5? That would be 55 hertz. Okay. Looking at number 1 here, it says mark the nodes and antinodes for harmonic 5. Okay. Mark the nodes and the antinodes for harmonic 5. Okay, so zooming in right here at the fifth harmonic, let's mark the number of nodes and antinodes. Okay, so that's a node, 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 that's a node. Okay, so we have 1, 2, 3, 4, 5, 6. We have 6 nodes, right there. So we have 6 nodes. And how many antinodes we have? Well, that should be obvious because if we're the 5th harmonic, that means we always have 5 antinodes. So 5 antinodes. You guys should be able to see this here. This region, that's an antinode. That's an antinode. That's an antinode. That's an antinode. And then that's an antinode, right? So, this point right here and this point right here, those are points of maximum displacement. Maximum displacement, maximum displacement, maximum displacement, maximum displacement. So here we have 1, 2, 3, 4, 5 antinodes, which makes sense if we are at the 5th harmonic. Okay. I'm not going to worry about marking wavelengths or anything like that, because that's not important for the assignment. All right, guys, I just want to do just a few more on the back here. I want to fill out these blanks here. I just want to fill out enough of these blanks so you guys can understand what's going on here. Okay, so the first harmonic has how many antinodes? We just stated this earlier. The first harmonic it always has 1 antinode. The third harmonic has 3 antinodes. For something that's vibrating at the 8th harmonic, that would have 8 antinodes. Okay, so that was something that we stated earlier. Okay. The first harmonic has 2 other names. Okay, so guys, there are 2 names that you can use to describe the first harmonic. One, you can describe it as the fundamental harmonic. Fundamental harmonic. Hold on, let me write this better than this. Give myself enough room. So the first harmonic can either be called the fundamental harmonic or the fundamental frequency. Same thing. Or guys, another term that you'll see for the first harmonic is what is known as its natural harmonic or its natural frequency. On the homework assignment, you'll see those terms used interchangeably. They both mean the first harmonic, either the fundamental harmonic or the natural harmonic. Okay. So look at this right here. It says, if the fundamental frequency is 20 hertz, find the third harmonic, or H3. Well, if the fundamental frequency, in other words, the first harmonic is 20 hertz, you would just do 3 times 20, and that gives you a frequency of 60 hertz for the third harmonic. Okay. So what about this right here? If the natural frequency is 8 hertz, find the 5th harmonic. In other words, find H5. So what is 5 times 8? Okay, 5 times 8 will be 40 hertz. Okay. If the 4th harmonic is 48 hertz, find the fundamental frequency. Well, 48 times well, no, we're not times. We're not multiplying here. We're actually dividing because we're going backwards. Notice here, they gave us the 4th harmonic and they want us to find what is the first harmonic or the fundamental harmonic. So in this case, we would do 48 divided by 4. So 48 divided by 4 will be 12 hertz. Okay. If the third harmonic is 12 hertz, find the fundamental frequency. Well, so what's 12 divided by 3? That is, in this case, this is 4 hertz. Okay. All right. I'm gonna do one more section, and then that's this section right here. And after this last section, I'm gonna let you guys go. Okay. So guys, look at this diagram here off to the side. What harmonic is this? Y'all should be able to look at this and to know what harmonic is this, because look at it. Let's count how many antinodes we have. We have 1, 2, 3 antinodes. So clearly this is the third harmonic. Okay. mark the nodes and the antinodes. Well, so the nodes, here are nodes right here. Okay. And then these points right here are antinodes. So that's an antinode, that's an antinode, and that's an antinode. No, okay. So I'm not going to worry about marking one wavelength because that's not going to be on the assignment. Find the object's natural frequency. Guys, remember what natural frequency is? Natural frequency just represents the first harmonic. Okay, notice here if our frequency is 45 hertz at the third harmonic, then how will we find the frequency at the first harmonic? Well, we would just do 45 divided by 3, right? Because here the harmonic number is 3, so the frequency at the third harmonic is 45. So 45 divided by 3 gives me 15 hertz, right? So this will be the natural frequency, or in other words, the frequency of the first harmonic. Okay. Find the frequency of the fourth harmonic. Well, we would just do 15 times 4, right? So 15 times 4 will give me the frequency of the fourth harmonic. So 15 times 4 will give me 60 hertz. Okay. Everybody got that? I think I'm going to stop there. Okay. Any questions? Okay, before I let you guys go, remember what I said. For any object vibrating at the first harmonic, always has one antinode. If it's vibrating at the second harmonic, it has 2 antinodes. If it's vibrating at the third harmonic, it has 3 antinodes, and so on. So basically, the harmonic number tells you the number of antinodes that you have. Okay. And remember, the number of nodes is always one more than the number of antinodes. So if we can guarantee that we have 3 antinodes, for sure, we can guarantee that we have 4 nodes. Okay. So because this number is always one more in addition to that number. All right, guys. If y'all have not filled out the attendance form, please do so now. Guys, I'm going to post this video on YouTube, and also the link to that website that I showed you guys today that basically gives you a visual of the harmonic number. I'm going to also put that link in YouTube as well. And of course, give me about 5 or 10 minutes or so, and I'm going to have the assignment ready for you guys to take. If you guys don't have any immediate questions for me at the moment, you guys are free to go. Have a good one, everyone.